Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our discussion about solving trigonometric equations and specifically using the sum to product formulas. Now, these are very rare equations to come across, at least in textbooks. You'll see them in pre-calculus every once in a while, but they're not ideal equations to work with because when you look at an equation like this, it is actually somewhat challenging to realize that this is going to be a sum to product formula. So let's at least start this problem and kind of ferret our way around, try to figure out how to do this. Let's suppose that you didn't know you were supposed to use a sum to product formula here, and you're just staring at this. Remember, the sum to product and product to sum formulas are not usually memorizable. So if they occurred, let's say on an exam, you would be given all 8 of those formulas if they were needed. If they're not needed for the exam, you're likely not given those. Now, your instructor might be slightly different. So they might require you to memorize those. So you might want to double check with your instructor. Let's suppose that you didn't know, however, that you're supposed to use a sum to product formula. For this problem, you could still possibly get away with it. The idea here is you have 3 different trig functions. Well, you have 3 of the same trigonometric functions. They're all cosines, but their arguments are completely different. So the first one has an argument of 4 theta, and then we have a 2 theta and a regular theta. It's easier to decrease an argument to a smaller argument, so from a 4 theta to a 2 theta and a 2 theta to a 1 theta, than it is to increase an argument. So I would rather go ahead and decrease these cosines of multiple angles into cosines of single angles. So I'll start with the cosine of 4 theta there. And this is just an experiment because I'm not 100% sure that this will actually decrease in complexity by doing this. So notice what I just did. I wrote that's the cosine of twice an angle, essentially. And over on the second term, I happen to know what the cosine of 2 theta is. We have 3 versions of the cosine of the double angle. Cosine of 2 theta, if you will recall, is either cosine squared of theta minus sine squared of theta. This is totally memorizable, by the way. Or it's twice cosine squared of theta minus 1. Or it's 1 minus twice sine squared of theta. In this case, because everything is currently written in terms of cosines, I think I'll go ahead and go with that middle formula. So that cosine of 2 theta, I'm going to trade out for a 2 cosine squared of theta minus 1. Let me go ahead and write that in. 2 cosine squared of theta and then minus 1. And we still have on the right hand side a regular old cosine of theta. And this starts to look somewhat promising, at least everything except for this first term. Now that first term can be reduced, right? It's the cosine of a double angle. Just pretend as though that highlighted factor there is just some angle alpha or whatever. Well, I'm going to use the same formula. So the cosine of twice an angle is twice the cosine squared of the half of that angle, which is 2 theta. So cosine squared of 2 theta and then minus 1. And then we have plus 2 cosine squared of theta, again, minus 1, and this is equal to the cosine of theta. Again, this is totally an experiment because this might not actually work. Well, at least the minus 1's combine, right? So we could at least do that. So I have 2 times the cosine squared of 2 theta plus 2 times the cosine squared of theta and then minus 2 is equal to the cosine of theta. The final step, I'm going to trade out that cosine of that double angle because now you can see the vast majority of our terms with cosines involve cosines of single angles. So I'm going to trade out that cosine of the double angle for, again, a 2 cosine squared of the single angle minus 1. Notice what I did there though. It's the cosine squared of the double angle. So what I did is I went ahead and wrote a bracket out the back end there and just said, whatever that cosine of the double angle turns into, I'm going to have to square that. And that is a problem, possibly. I'm not 100% sure still, but let's just pretend. We keep moving down here and we get all the way down to this point, and you distribute out that binomial right there, and you multiply everything by 2. So let's go ahead and do that. That binomial distribution would give me a 4 cosine squared, but we're multiplying it by 2, so it's an 8 cosine to the 4th. Sorry, is what I should have said. It was going to be a 4 cosine to the 4th, and then we multiply it by 2. We would also have a negative 2 times, or negative 4 cosine squared, and then times the negative 2 would be a negative 8 cosine squared. And we'd have a positive 1 times 2 is a positive 2. And we still have a positive 2 cosine squared of theta, and minus 2 and equals a cosine of theta. The nice thing about this, again, total experiment, I didn't know if it was going to work out, but it does actually. Those 2's cancel. I can move that cosine that's on the right hand side, this guy right here, I can move over to the left hand side via subtraction, and also I can combine like terms on the left hand side. So the left hand side is going to be the 8 times cosine to the 4th of theta. I have a negative 8 cosine squared plus 2 cosine squared, which is a negative 6 cosine squared of theta. And then I'm subtracting a cosine of theta from both sides because the right hand side, I just moved that cosine over. And you can see all 3 of these terms have a cosine in common. So you could technically factor out that cosine and you're left with 8 cosine cubed of theta minus 6 cosine of theta and then minus 1. And you're kind of shut down at this moment. There's not much you can do with this trinomial at the back end. Well, okay, so technically speaking, if you're in a pre-calculus course, you might be able to. If you just, as an aside, I'm going to write this in blue. As an aside, if you let, let's say x equal the cosine of theta in that term, or that factor, which is 8 cosine cubed of theta minus 6 cosine of theta minus 1, you would get 8x cubed minus 6x minus 1. And I'd love to see if that factors. Well, you could use the rational roots theorem. Again, this is if you are taking pre-calculus. If you're taking trigonometry and you likely have not seen the rational roots theorem, you're pretty much stuck right here. There's nothing you can do. But at least in pre-calculus, you might be able to dive into the rational roots theorem to see if you can find some zeros of this polynomial. And to do so, notice it has integer coefficients. To do this, we take a look at the factors of negative 1 and we take a look at the factors of 8. In other words, we take a look at the factors of the constant term, which are technically just plus and minus 1, and the factors of the leading coefficient, which is 8. And numbers that multiply into 8 are plus or minus 1, plus or minus 2, plus or minus 4, and then plus or minus 8. And then you would do synthetic division to see if any of these is actually a root. Now the plus or minus, so I shouldn't say any of these, I should say you have P over Q, which is the ratio of all these. So it's plus or minus 1 over plus or minus 1, which is plus or minus 1. It's a plus or minus 1 over a plus or minus 2, which is a plus or minus 1/2. Plus or minus 1 over a plus or a minus 4, which is a plus or minus 1/4. And finally, plus or minus 1/8. And you could test to see if any of these are roots. Again, only if you've had pre-calculus. right? Because you likely are, if you haven't had pre-cal, you're just staring at this going, what the heck is he doing? One thing that we know from pre-cal is that if you plugged in a 1 and this becomes 0, then 1 is a root. So x minus 1 is a factor. Well, try plugging in 1 here and you'll find out it doesn't become 0, right? That'd be 8 minus 6 minus 1, or in other words, 1. So positive 1 is definitely not a 0. So then you try negative 1. Well, negative 1 is also not a 0. If you tried to plug that in, that wouldn't work as well. So those two are gone. You could try plugging in halves, but it's actually a little bit easier at this point to just use synthetic division. So if I use synthetic division with a half, 8x cubed, 0x squared, negative 6x, and a negative 1, you could quickly use synthetic division here, bring down the 8, multiply it by half, that becomes a 4, add the 4 to the 0, multiply it by a half, it becomes a 2, add that to negative 6, it becomes a negative 4, multiply it by half, it becomes a negative 2. You add that up, it's not 0. That's the important part. So positive 1/2 is definitely not a root either. So then you go to a negative 1/2. So let me put a negative on here and let me just sweep out all of my previous work. You bring down the 8, multiply it by a negative half, it becomes a negative 4, add those together, multiply that by a negative 1/2, it becomes 2, add those together, right? And you multiply that by a negative 1/2, it becomes a 2, and that's non-zero. So again, that's out of play. Now I'm going to deal with the plus 1/4. You could see all the work that you're doing to try to get this to factor. The reality is that you could spend quite some time doing this, but it's good actually this late in a pre-calculus course to go ahead and continue this problem, because it's good to remind you that you do have the rational roots theorem at your disposal. So bring down that 8. We're trying the 1/4 as the root here. 1/4 times 8 is 2. 2 plus 0 is 2. 1/4 times 2 is 1/2. 1/2 plus a negative 6 is a negative 11/2. And you can see when I multiply this by 1/4, it's some number here, but it's not 0. So again, positive 1/4 is out of play. So then you move to the negative 1/4. And negative 1/4 will likely not work either. Bring down the 8, multiply it by a negative 1/4, you get a negative 2. Add those two up, you get a negative 2, multiply that by a negative 1/4, and you'll get a positive 1/2, and that's 13/2. And you can see this is some number that when you add it to 1 is non-zero. So we are done with that. Well, I was going to stop much earlier, but I might as well just finish this out, right? You'll see that this will not work. I can kind of see it's not going to work, but let's just pretend, right? So 1/8 times 8 becomes 1, add it up, right? And now when I multiply by 1, I get 1/8, and this is some fraction, terrible fraction, negative 48/8, negative 47/8. And multiply by 1/8. This is some number, but it's not going to be 0 when you add it to negative 1. And I'm going to guarantee negative 1/8 also will not work. So all of that work to try to solve this equation, and it results in a stall. Now, again, you could double check all our mathematics here, but everything does work out beautifully. Everything's very nicely done. The only thing that, let me just double check. Yeah, I just went through and double checked everything's correct here. So the only thing that I could say is that, well, obviously using double angle identities are not going to help here. So I will go ahead and cross this out and maybe go into a different technique. And the only other technique that might help here is going to be the sum of angles formula. And that's how obscure the sum of angles formula, or sum to product formula is what I meant to say. That's how obscure it can be to use, because the sum to product formulas just don't get used so much. So the cosine plus cosine is what we're looking at. And if you don't recall, that's totally fine. I don't blame you. The cosine of an angle A plus the cosine of an angle B, which is the formula that we have on the left-hand side of that equation, is going to be twice the cosine of the sum of those angles divided by 2 times the cosine of the difference of those angles, again, divided by 2. So if you take advantage of that formula, then our equation becomes twice the cosine of the sum of 4 theta and 2 theta divided by 2. That's 6 theta over 2, or 3 theta, times the cosine of the difference of those two angles divided by 2. 4 theta minus 2 theta is 2 theta. Divide that by 2, it becomes a regular old theta. And this is supposed to equal the cosine of theta. Now look how nice that is, because we can actually move everything over to the left-hand side. So we subtract cosine of theta from both sides. And you can see both of these terms have a cosine of theta in common. And that would be twice cosine of 3 theta minus 1. Oops, equals 0, not theta. And so this is now somewhat easily solvable, right? We have the cosine of theta is equal to 0. Or 2 times the cosine of 3 theta is equal to 1. I'll just say it that way. Dividing by 2. Just get this. Oops, I didn't write equals 0. Now that equals 0, that's an axial ratio or a quadrantal ratio. So I'm just going to quickly graph out the cosine curve so we could see where the cosine becomes 0, which is at pi over 2, and 3 pi over 2, and then 5 pi over 2, and so on and so forth. So the infinite number of solutions to this equation is going to be theta is equal to pi over 2 plus pi k, where k is an integer. And now we'll go to the second equation there. And the second equation, well, this is all about reference angles and quadrants. 3 theta hat. The cosine of what angle gives me 1/2? Well, you should know at this point, now that we've done this enough, the reference angle should be pi over 3. Cosine of pi over 3 is 1/2. And cosine is positive in quadrants 1 and 4. So our cosine, or the solutions to this equation, in quadrant 1, reference angle of pi over 3, that means the actual angle, which is 3 theta in this case, our actual angle is going to be pi over 3 plus 2 pi k. Again, k is just in the integers. But that's not what they're at. They want to know what's theta. Theta is the unknown. So let's divide both sides by 3. And to get theta is equal to pi over 9 plus 2 pi over 3 k. So that's our quadrant 1, our solutions arrived at from using the quadrant 1 solution. How's that? And then the quadrant 4 solution, it is, if you're not using an online homework system, it is totally fair for you to say that if you're in quadrant 4 with the reference angle of pi over 3, your actual angle is a negative pi over 3 plus 2 pi k. That is totally fair if you're not using an online homework system. But in online homework systems, they often want your initial angle there, that negative pi over 3, to be between 0 and 2 pi. So in quadrant 4, with the reference angle of pi over 3, and you're using an online homework system, I would use 5 pi over 3 because that's a quadrant 4 angle. It's between 0 and 2 pi. And now, dividing both sides by 3, you get theta is equal to 5 pi over 9 plus 2 pi over 3 k. We can box up these solutions because we didn't square both sides or anything like that, so there's none of these are extraneous. So I'm just boxing up all the solutions here, and we are done with this problem. So it's a really good problem to showcase that if you can recognize or remember that you have a sum to product formula, it is very powerful at times. Not a lot, but not often, but it can be powerful. I will have students that when I go through this material, they ask, well, what about the product to sum examples? Well, it turns out you won't have product to sum examples in equations. Or if you do, I've never seen one. And the reason is fairly simple. If you had a product of two functions, let's just say it was a sine and a sine, okay? If it equals 0, well, let's say it's sine of A times sine of B. If it equals 0, then either sine of A is 0 or sine of B is 0, and you're done. If it's not equal to 0, so let's just say it's equal to some number, actually, I'll call it n. If it's equal to some number n, well, then you have to actually use the product of sum formulas here, or if you think you should use the product of sum formulas, you would get the following. You would get 1/2, and the sine of A times the sine of B is cosine of A minus B minus the cosine of A plus B. And this is supposed to equal n. You multiply both sides by 2, and you get to this point, and you're kind of locked, actually. You're now just really stuck. And so you would, again, go back to compressing this down to a sum to product formula. So really, you're not going to go from a product to a sum when you're solving equations, because you don't really get good solutions that way. So that's just a heads up. Yeah, you're not going to run into that. All right, I only did one example in this video, but it's just more of a reminder that you have those formulas if you're in pre-calculus, or if you have a full trig course. A full trig course should cover this. So heads up, there you go.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.